All right, so we're going to look at gravity and some applications of gravity to kind of go along with the things that we talked about on Wednesday. Again, if there are any questions about any of the problems that you're working on, please don't hesitate to send me a message. We will talk more about these hopefully on Monday. Hopefully we'll be in school. Okay, so one point to make. A spherical mass exerts the same gravitational force on masses outside it as if all the mass on the sphere were concentrated at its center. And so what we're saying is that the center of mass is going to be smack dab in the center of the object, okay? So the force on mass is outside as if all the mass sphere were concentrated at its center. So as we look at this, here's our planet. Let's say it's the Earth, right? And we have this small object here, and we have this. This object obviously is going to be coming towards the Earth, all right? And this force is going to be equal and opposite, right? Newton's third law. So we know that. So we know the gravity force of the big object on the small object is equal to the force of the small object on the big object, just going in different directions. But we want to figure out the acceleration, g, of this small object. And so we take this equation, which is our universal gravity equation, and we start solving for some things. So F is mg. So that gets substituted in for F. When it happens, our m's, our small m's, can get crossed out, right? So now if we want to solve for g, and this is an equation that's useful, if we want to find the acceleration due to gravity of any planet, okay, we're talking about Earth here, but it can be of any planet, we take the gravitational constant times the mass of the Earth, or mass of the planet, divided by the radius of the planet squared. And g will be the same anywhere on the surface of this planet because the radius is going to be the same. All right? And this is where that 9.81 comes from mathematically, and you can see the numbers here to support that. But that's how we can use the universal gravitational equation to find the acceleration due to gravity. And this can be any planet. If you know the mass and the radius of the planet, you can find g at its surface. So let's talk about an application. Let's say we climb to the top of Mount Everest, or you do, not me. I'm too old. That has this height, okay, above sea level, and we want to know what g is up here, okay, g at the height. So the first thing I want to do is, like I did before, force is equal to g little m, which is me, big M, which is the Earth, divided by the distance traveled squared. Now, this distance, you got to think about this. This distance is the radius of the Earth. That's to sea level. But then we're also going up that far above sea level. So our radius is going to be radius of the Earth plus the height we climb. Okay? So that's going to look like big G, little m, me over the radius of the Earth plus the height, and all that squared. And luckily we know all those numbers. Going back to what we previously showed you, our force is mg, right? So little mg is equal to g, little m, mass of the Earth, over radius of the Earth plus our extra height of the mountain squared. These little m's cancel. Now I just substitute. So I go big G. Mass of the Earth is a known number. I'm going to show you maybe a little bit how that can be derived. It's 5.97 times 10 to the 24th kilograms. And I'm going to divide that by the radius of the Earth, which we know to be, on average, 6.37 times 10 to the 6th meters, plus 8850 meters, all that squared. So we punch in g is 6.67 times 10 to the negative 11. We know that number. We'll talk about how that was derived also today. But when we do the math of that, we get little g at the top of Mount Everest to be 9.79 meters per second squared. Interestingly enough, the farther we get from sea level, the less we're going to accelerate when we fall. And that's because we're not as close to the center of the Earth. All right, so let's look at acceleration due to g at different points here. So this is our height in kilometers above, right? And this is where we're at sea level. And then you can see, here's where Everest is at. Here's the International Space Station. So if I extrapolate here, at the International Space Station, approximately by close to 9 flat is what G would be. And the acceleration due to gravity far from the Earth, you can see we get a nice parabolic line that forms. Okay? And that's because of the r squared at the bottom, right, of our equation. But you can see a lot of our satellites are almost at less than 1 G when we talk about acceleration. But that's just some graphing to get a feel for how G changes based on distance. So if we want to find the moon's gravity, so this is our equation to find G for anything, right? The constant times the mass of our planet, satellite, moon, divided by the radius squared of that object. So for the moon, I would use this equation. I'd put the mass of the moon divided by the radius squared of the moon multiplied by the constant, and that would give me the acceleration due to gravity on the moon. So let's find the acceleration due to gravity on the moon. So G on the moon is equal to big G, mass of the moon over the radius of the moon, all squared. All right, big G, we know that number. Mass of the moon's given to us in the problem. 7.35 times 10 to the 22nd kilograms over the radius of the moon, 1.74 times 10 to the 6th meters, all squared. And we do all the fancy math, and we get G on the moon to be this. And believe it or not, you can prove that. I've seen it. Something we'll look at is we'll look at the moon videos and see if we can use G to find G using the moon videos. But this is what was figured out. So we did land on the moon, even though some people don't think we did. Okay, the next thing is the Cavendish Experiment. What I wanted to do was talk about this in great detail. Instead, since obviously I'm not there, you can read about it here, but there's gonna be another video clip in the agenda. All right, so that's going to explain how the experiment was done. Watch the video. If you have questions, we can discuss it a little bit more. I'm trying to find a good simulation so you guys can tinker with it a little bit, but right now I'm striking out. But watch the video, the extra video that's going to be on the agenda. All right. So here's how we can calculate the mass of the Earth if we know some things. So we take our equation, G times big T times the constant, mass of the Earth over the radius of the Earth squared, and we just solve it for mass of the Earth, which is that equation. Okay, so mass of the Earth is equal to, again, I'm going to go 9.81, 9.8, probably give you the same answer. The radius of the Earth, we've already established, is 6.37 times 10 to the 6th. That's going to be squared. That's in meters. And then we're going to divide that by our constant G, 6.67 times 10 to the negative 11. And when we do all of this, it's just the opposite. But again, using that equation, if we know the acceleration due to gravity, we can find other things. Okay, we can find the height. If we wanted to find if we know the radius of the Earth, we can find the height, which is a little more difficult math, but not impossible. There's a lot of things we can do mathematically because of our gravity equations, and because Cavendish found that constant. Definitely made Einstein's job easier. Okay, the internal structure of the Earth, we can use G and do a lot of things with that. One number that comes up is the average density of the Earth can be figured. I'm not going to bore you with the calculations. But you can see its mass over, we know the mass of the Earth, and we know the volume of the Earth. We can find the density, right? Now, of course, it's average. It's more dense at the core than it is on the outer layers. But, again, just something that we can find out based on information that we know. A black hole. So when we talk about gravity, we always got to talk about black holes. When a star dies and the mass comes back on itself, we start to see what's called a black hole. Now, by definition, a black hole is where something has so much mass and has so much a gravitational pull that light itself can't escape. So everything in the middle, all black. we even know that black holes, because of the pull of gravity, can actually bend light. And I'm going to show you something that kind of proves that, at least theoretically, that we've seen in space. So a black hole is when something so massive, a star, collapses on itself, dies, all the mass comes in. When that happens, light doesn't escape, so that's why it's black, but it also bends the light around it. This leads us to something that's called gravitational lensing. So let's say you're on Earth and you're looking at space and you see this galaxy cluster, and then there's a distant object you see. All right, this galaxy cluster has a boatload of mass to it. All right, and so just talking about Einstein and his theory of relativity, he predicted that any amount of mass can bend light. Now, light that we see here is so minimal when we talk about the bending that we don't see it as much. But when we talk about something that far away, all right, so like if it's past an entire galaxy of stars, especially if there's a black hole, especially if there's a black hole in the middle of the galaxy, which there probably is, what we see is that this can get bent in large amounts, all right? And when we see this, what happens is that the galaxy or black hole changes the direction of the light, just like a lens or something would if we were using reflecting light with a lens. And because of lensing, from Earth, what we see is not only this object, but because of the bending of light, we actually see multiple images. So we see sometimes 3, sometimes 6. I mean, it can be quadruplet, it can be spread out in an entire circle, depending on the gravitational pull of the light. But this bending of light by this huge mass in the galaxy makes us see different images of the same object. So the object is here, but we see 3 different objects in space. So we see more than what's really out there. Kind of groovy, huh? That is all.